Hey students, welcome back. If you check out the fossil I've got in front of me right here, across the hall you're going to hear from Mr. Westbrook when he's doing social studies, things about the Maya, things about the ancient Egypt, and one of the things that they will constantly bring up is how old an artifact is. Remember, the overarching theme in this class is evolution throughout the entire year, and bringing these things together. When we were talking about how old once living things were, we've got a wonderful tool in science to figure out how old once living things are, and it has to do with our understanding of the atom, has to do with something called radioactive decay. So as we go through our biology book, we take a little turn here. Now we're not going too deeply into chemistry. We're not going to be balancing chemical equations too much, although we will show a balanced photosynthesis equation because that gets, of course, to conservation of matter in a chemical reaction. But the point is we have to know a little bit of chemistry as we talk about proteins, lipids, nucleic acids. The book, the text, the subject area requires us to know a basic understanding of chemistry in this class. So let's jump on into what we did today, what's due, and where we're going with this. First of all, we talked about isotopes, specifically carbon-14. You can think of it as a flavor of carbon. And if you look at this right here, this fossil right here, you've got a predator fossil. Now, when that animal was alive, it was breathing, eating, taking in carbon all the time. And through our understanding of chemistry, and again, this is why we're reviewing protons, neutrons, electrons, how atoms are put together. Through our understanding of chemistry, we know that almost every single carbon atom that animal brought into its body when it was alive was carbon-12, the average everyday carbon that you run into on the periodic table. Every once in a while, it would take in a radioactive form of carbon, just like we do when we breathe or we do when we eat, called carbon-14. Now, here's why we're learning about isotopes. It's why it's one of our key terms this week. When we look at isotopes, it's just a type of that particular element. It's a flavor, if you will, of carbon. It's a particular form of carbon. Most of carbon is not carbon-14. Most of it is carbon-12. If you're wondering, it gets that number because it's got 6 protons, 6 neutrons, 6 and 6 is 12. Every once in a very long while, when you run into one with 6 protons, that's what makes it carbon, and 8 neutrons, you've got a form of carbon that is radioactive. And we know how fast that carbon breaks down over time because it breaks down at a regular rate, and we can test that. Here's the upshot. Here's where we use it in biology class. Here's where Mr. Westbrook across the hall will use it to tell you how old, say, a fossil is that they found from the Maya civilization or from ancient Egypt. We can take a sample of a once living thing. Now, it doesn't have to be a bone, for example. It could be wood from a campfire that we found. This is how we know, for example, how long ago people came to North America. And we can say, okay, once that thing died, whether it be a tree, this bone here of this small coyote, we have all of a sudden stopped taking in any more carbon. And so the radioactive carbon that was taken in by that animal or taken in by that tree, it will start to slowly decay over time. If we know the regular rate and we compare the ratio of carbon-12 to carbon-14, we have a very, very accurate way of dating fossils, things that were once alive, which is awesome. Now, carbon-14 works for once living things. We're going to learn later on in this class, especially when we do a little bit more with Darwin and geology, the laws of superposition, things like that. Sometimes carbon-14 doesn't work. We're going to use other radioactive elements that are up on the periodic table. I'm pointing at the periodic table that's across my classroom. So that's why we're learning about atoms. That's why we're learning about the structure of atoms. Again, for this class, we're not going too deeply into atomic shells. We're not going too deeply into balancing equations, but we do have to have a basic understanding of the periodic table because it helps us understand the slow change of life over time. If we're looking at this right here, that was the first part of the class today when we're checking out the brain pop. The lab write-up today, what I'm asking students to turn in tomorrow looks a little bit like this. We, in class, again, this is a great way of teaching control variables, experiment variables. We were taking a pendulum and we were swinging it back and forth. And we wanted to see how long one single swing took. Since it's really difficult to time one single swing, we would time 10 swings, see how long that took, and then divide by 10. Here is the data when we put it into a graph. We do 3 trials, and we take our average. Now, when we're taking our 3 trials and we take our average, our next step is going to be to put it on a graph like this. I'm trying to lead the students into seeing that this looks very, very familiar to what we saw with Hubble's data. Remember Hubble? This goes way back to the beginning of the class, all those, 5, 6 weeks ago. You might remember we were saying, well, how do we know the universe is 14 billion years old? How can we possibly know something that happened that long ago? You remember Hubble took the data and it basically made a straight line. There was a real connection between the independent and the dependent variable. Basically, as he was looking further out into space, he was seeing things move faster and faster and faster away from us. This gave us the clue that everything was back together at one place at one time. If you run the clock backward, it showed that our universe is about 14 billion years old. Getting back to this data right here, the students will notice when they start putting the data on the graph that it makes a fairly straight line. In other words, as the string length increases, the period, the time for one complete swing out and back, that's one period. The time for one complete swing out and back will also increase. Now, the nice part about this, and this is what we're trying to lead the students to this week, is this is predictive. It allows us to make predictions. At the California Academy of Sciences, there's a huge pendulum that swings back and forth. You might have seen it. It's got a huge, huge ball with a point at the bottom that knocks over pegs at regular intervals. And based on the data here, we should be able to figure out exactly how many meters high that pendulum is. In other words, we're looking at linear data right here. Did the length of the string change the period of the pendulum? Yes. And we had a fantastic online simulation that I'll link down in the notes that shows as you increase the length of the string, you increase the period of the pendulum. Does the mass change the period of the pendulum? This goes right back to the very first week of school when we did a first mini lab on falling objects. Remember Galileo supposedly taking heavy and light objects to the Leaning Tower of Pisa? Whether that's an apocryphal, made-up story or not, doesn't matter. We know that objects of different mass, if you disregard air resistance, fall at the same rate. Remember the famous picture we showed, I believe it was Apollo 14 that was up on the moon. It was, and I get to double check that, it was the Falcon. When it was on the moon, he took a hammer, he took a feather. There's no air on the moon, dropped them. They both fell at the exact same rate. They both hit the lunar dust at the exact same speed. Why? Well, there's no air to slow down the feather. It didn't flutter down on the moon. It fell at the exact same rate as a very heavy hammer and a very, very light feather. Again, confirming Galileo's idea that objects of different mass fall at the same rate. Going way back to Aristotle. Remember Aristotle said, heavier things fall faster. Galileo, this is why in the second week of school we started talking about Galileo and the scientific method. Turns out that when we test these things, we put them on a graph, we can find out not only that heavy and light objects fall at the same rate, but we can predict. That's the key to putting things on an independent and a dependent variable graph. It allows us to predict data that we might not have yet. For example, going back to Hubble one more time, he was able to predict very, very accurately, like, hey, we don't have telescopes good enough right now to see that far into space. But when we do, I bet, when we see data that shows very, very distant galaxies, we can probably very accurately be able to predict the speed with which that galaxy is rushing away from us. And it turns out, it makes a nice straight line. It's a predictive graph. That's what we're doing here in science. We're trying to show not only Galileo and a bunch of facts. We're trying to show how it is, what we know, and to that end, getting back to the very, very beginning where I started, we're talking about the evidence for evolution, and we're talking about evolution being the overarching theme to this class, understanding a little bit about chemistry, about atoms, and about how they're put together, and how radioactive decay occurs. This gives us strong, strong evidence. One of the strongest pieces of evidence that we have for evolution occurring on this planet over the last 3.5 billion years. That's where I'm going to leave it today. Please make sure you get your lab write-up done tomorrow, for tomorrow, to turn on in. Again, you're taking your data, the 6 string lengths from class in centimeters now, the 6 string lengths in centimeters, the time for a single swing on those pendulums, and you are putting that data onto the graph. If for some reason, and we had 2 days in class to do this, if for some reason you don't have the data from class, get a string and any weight at home and do it yourself. Just remember that we're using centimeters. Remember, the amount of mass at the end of the string will not change the period. The string length will, and what we want to be able to do is predict by putting the data on a graph. All right, that's where I'm going to leave it today. Take care, everybody. See you online.